Hi all, we are Team 11. We are presenting mixture of experts model for code creation. Currently, ML-driven multilingual code generation faces a problem of creating low-quality code. Existing techniques rely on models of monolithic architecture, which does not work well. However, our team has created a robust framework that leverages the concept of mixture of expert. This new solution has greatly improved the accuracy of code generation across multiple programming languages. Our work is significant because high quality automated code revolutionizes coding tools, speeds up software development cycles, and reduces costs for tech driven companies. The primary dataset we used was CodeParrot from Hugging Face. It contains instruction code pairs in 7 programming languages with approximately 10K rows per language. The data is representative of typical coding tasks encountered in real world software development. We filtered the data points to 4 coding languages specifically, which are Python, C++, Java, and JavaScript. So what on earth is mixture of expert? Mixture of expert essentially divides a complex model into smaller models yet with more specialized domain knowledge and unites them. The first step is to choose a complex baseline model. We selected Mistral 7B because it excels in compute efficiency and performance, surpassing GPT 3.5 and Llama 270B in areas such as code generation and multilingual translation. So at the second step, we fine-tune the Mistral model based on a subset of our datasets, which contains one of the programming languages, and we iterate through all 4 languages. The purpose of this is to create 4 models that become experts in each of the languages. There are 3 techniques that play an important role during this step. First, this is a supervised fine-tuning process. It is widely used to adapt a pre-trained LLM to a task-specific downstream using labeled data. Second, we use LoRa because this technique improves the efficiency of fine tuning by changing the weights for adapter layers while keeping the original model parameters frozen. Third, we know training LLM could exhaust extensive compute resources, so we quantize our models into 4-bit.
So in this step, we united the expert models into one single model. This architecture also consists of a key component known as the routing network, which identifies and selects the most suitable expert model for the input task to yield the corresponding output. The expert selection is based on the hidden representation of the input prompt. So we use a technique called dice merging, which is designed to specifically efficiently merge multiple task-specific models into a single multitask model. It addresses 2 main challenges in model merging. One is the redundancy in model parameters. Another one is disagreement between parameter signs. Dice merging is divided into the following 3 steps. One, starting from trim, sign, and disjoint merge. Unlike the other methods, dice can merge multiple models at a time. When we feed a prompt that expects a Python code snippet into the MOE model, the router selects the Python expert model and produces the correct output. So how well did our solution work? So we used a metric called CodeBlue to evaluate it. CodeBlue calculates the weighted n-gram match score and syntax score, the output and the reference solution. It matches the output and the reference solution. So intuitively, the higher score, the better. We calculate the CodeBlue score on the baseline Mistral model using each language separately as benchmarks. And then we calculate the score on the fine-tuned model. We can see that the improvement is quite obvious. For example, the CodeBlue score of the baseline model on Java dataset is 0.19, but the score of the fine-tuned model is 0.43, which is a huge improvement. Then we test our model on the whole dataset, including all 4 programming languages. The accuracy went from 0.166 to 0.25. Here are our findings. So our fine-tuning achieved high performance in Python, Java, and JavaScript because these languages have consistent language structure and explicit syntax. What is surprising is that C++ expert model didn't improve as much as we anticipated. Possible reasons are language complexity and overwhelming syntax and error propensity. However, in general, mixture of experts achieved high overall score since it is like a 51% huge improvement compared to the original raw model. So the key takeaway from this project is the MOE model excels in code generation, notably improving output for multiple programming languages. Expert networks provide language-specific expertise, especially enhancing Python and Java code quality. So the real-world impact is MOE model streamlines code generation, offering time and cost savings in software development. Broader range to access the MOE technology could catalyze the innovation across various industries. Future directions, focusing on refining the C++ model and other underperforming programming language model. Expand the MOE to cover more programming language for wider use case. Thank you.